Hello, my name is Thilo Muth. I work in the section of eScience at the Federal Institute for Materials Research and Testing. And today I want to give you a presentation on the title Beyond the Buzzwords, a guide to sustainable software development in research. And some of you might still know these kind of blue screen errors that happened in the 90s very often when I was young, and there was like Windows 95 and Windows 98 and these kind of operating systems. And actually that does not happen anymore that often today. So modern operating systems, they are quite stable. And also, in general, like software tools that are have an industry standard are very solid, and frequently you get a freezing screen or something like this. But what's the case in research? In research, you actually find many of these problems or bugs still in software tools. And why is this the case? Well, there are some aspects on that. One is that research software is developed in a quick and dirty programming manner. So researchers teach themselves and learn to program on the fly. They are rarely computer scientists or mathematicians with a solid programming background, and the software and the methods that they develop, they fulfill a specific purpose or address a certain research question, and then actually it is often forgotten. And then as well, there's a code then fix mentality. So there's no comprehensive testing performed, and also there's a lack of time and resources. There's no software maintenance and support. And also the researchers themselves, they have no intention to reuse. So this is often a software prototype that is used as an in-house script or as an in-house tool, and it's not always released or published. So these are typical problems in research software development. So what's the problem about this? The problem is that with these kind of research software development, you will have a problem of reproducibility and also sustainability of these kind of tools. And as you can see here in this questionnaire, what factors contribute to irreproducible research? There are some of the typical things that are stated is like pressure to publish, low statistical power or poor analysis, poor experimental design, for example. But there's also a significant part from this kind of questionnaire where the answer methods or code are unavailable. So unavailable software code is part of the scientific reproducibility crisis. So we know this problem of the reproducibility crisis, and we know the problem that software is often unsustainable in research. So what to do about it? And there were experts already sitting together with this problem and with the question, what is critical for software development good practice? And these experts set up a top 10 metrics, in this case for life science software good practices. And there's metrics like, is a version control used? Is the software discoverable? So is the software actually available as an open source tool? Is an automated build system used? Are test data available? So these are the typical metrics, and they ranked it based on the fact of how important these measures are and how easy to implement. And based on these metrics, you can already see that there are some easy measures that you can take to make software and research more sustainable. So what is sustainable software by definition? Ideally, sustainable software should be correct, understandable, documented, released, and adequately published. So that means that is in a persistently identifiable form as a software source code. It should be actively maintained, and it should be reusable, usable, and adaptable. And in today's talk, I want to give you 7 of the best practices that you can directly use for your research software development. And the first one is access to software code is crucial. So as you have seen in the 2 previous slides, that there is a metric called the software should be discoverable. And that also means that your source code and not only your software is publicly available. And by doing that, the scientists and other developers can examine your methods and also give you valuable feedback. So this is a clear benefit also for you. When you start with the coding, when you're new to it, it's quite important to get feedback in the beginning. But even if you're an experienced developer, over time, you might get more ideas and other valuable feedback from other scientists and developers, and you can directly use it. The other advantage, of course, is that the source code can be used by others, so they will not have to reinvent the wheel again. And that's very, very important, that like when you have a software, a piece of software, put it out as fast as possible. Nobody will actually try to steal your code. Don't be afraid of that. As long as it's out, you can claim that it's yours, you can give it a license and so on. That's not a problem. And our institute, the Federal Institute for Materials Research and Testing, the BAM, supports the creation and use of free open source software for self-compiled software. So that means that it should be any kind of software that we develop should be open source by default. It's actually quite a nice thing that this is already supported by our institute. Then motivate your peers reading your code. Try to perform code reviews. So this can help you correcting and improving your code. Source codes may also be easier to understand also for reviewers than a complex method section in a manuscript. So that's why it's so important that you put your source code out as well. Method section in a manuscript, they can be quite complicated with some formulas, but when you read the code, then you understand your methods better. Others can understand your methods better. Second best practice, good code documentation is important. It's very important actually. So try to write meaningful comments while you're coding. Everybody should be able to read and understand your code. Of course, you know what the code is doing, but others may not know that, right? So when you give them some of these necessary and intuitive comments, they can understand your code better. Also, you need to keep the balance, of course, between too few and too many comments. So a bad example is here shown. If you have an incrementation of a variable and you just write increment value of I, that's not very, very useful, right? Also use embedded documentation systems. So there are like tools like Doxygen, NightR, IPython, and so on. So where you can really document within your coding. Do not document bad code, rewrite it. Very important. Third best practice. Try to code for humans, not for machines. Of course, your code is interpreted by the computer and used by the computer to fill a certain purpose, but the code is read by your colleagues, by other researchers, and so on. So these are humans. So try to make variables consistent, distinctive, and meaningful. That's the first one here. So a variable called foo is often written in tutorials and books and so on, but it is not descriptive. Not at all. Don't use that. Also similar names like result and result2 and result3 and so on. This is very confusing. Try to give them descriptive and consistent names. Stick to naming conventions and use consistent code style. So there are naming conventions, for example, here are shown two below: the camel case, which is very widely used in the programming community, and the snake case, which is quite concise when it consists of a few words, but gets a bit redundant when it's longer. But these are two naming conventions. Try to stick to them and use them consistently within your code. This makes your code much easier and easier to be understood. If you mix these naming conventions, of course, it gets harder again to understand your code. So don't do that. DRY, don't repeat yourself. Very, very, very crucial. Every piece of data that should be represented only once in your system, right? Try to avoid redundancy. And for example, physical constants, they should be defined exactly once, in the best case in the beginning of your code, so they are easy to find, and when you want to change them, that you can find them easily. But you define them exactly once to make sure that your whole software uses the same value. Try to also use unique identifiers, for example, for geographical locations from which data has been collected. Then modularize code rather than copy-paste. So try to extract methods and classes that you use very frequently and put them into modules, into libraries. And this also reduces error rates, because when you fix a bug once, once this bug is fixed at one place, the changes take effect in the entire code base. And the entire code base in the optimal case only uses this one method in a certain library, in a module. And you can also test and evaluate these methods separately. Code modularization makes code easier to understand and to be reused in other projects. Because these typical helper methods, things like parsing and so on, that might be used in many of your research projects over and over again. It would be nice to have it as a module that you can easily integrate it into upcoming projects and other software tools. Also, others can use them. When you think about these many libraries that are out there in Python and in other programming languages, it's always useful to take care that you have these libraries in place, that you use these libraries. So that's the last point here. Try to reuse code instead of rewriting it. Make your entire code base focused on libraries, on existing packages where many people contributed, for which many people already fixed a lot of bugs, and which are quite stable and frequently supported and used by the community. Next best practice is very typical in research in general. When you perform a PhD or a postdoc and you have a new research topic, then you need to go step by step. And the same you do when you're coding. Perform code changes incrementally. Use the force of agile development, that's how it is called here. So you work in small steps with frequent feedback, and also the possibility to change the course direction. Try to have a running code after each iteration, even if it's incomplete, but try to have it running. Very important here, that was the top number one metric in the experts workshop previously. Use a version control system. A version control system stores snapshots of project files in a repository, and it allows you to track the changes and also revert those changes. So if you have a problem, if you made a mistake, you can revert your code to, or the entire code base even. So besides source code, put everything that you have created manually in a version control system. So all methods data and source files for papers, try to put everything in a version control system if possible. Some examples here, typical ones are Git, Subversion, Mercurial. I think Git is now the most commonly used in nowadays software development and frequently used in research as well. So very frequently there's a big difference between industry-based software development and research software development. And this difference here is very obvious, that in research software development people don't use testing and build systems. The excuse is often, we don't have time for that and it should just fulfill a certain purpose and so on, as it was mentioned in the introduction already. But these systems are very useful and they allow you to plan for mistakes when you use them. Also, first of all, learn to use a debugger. I know many people who never use debugger in their life and they are even good coders, but if you're not a good coder, it will get very hard without a debugger. And a debugger is not just a printout. It's a system which is used within your programming environment, within your IDE. And it can be very useful because it can give you names and values, especially of variables, while you more or less emulate the running of a software. So learn to use a debugger, very important. Make use of automated testing environments. So these are the typical unit tests. And this is useful because you can actually test every method separately. Turn potential bugs into a test case. Use assertions. Just get familiar with test environments and use them wisely. It can be very, very, very helpful. Also automate repetitive tasks. So write bash scripts for command line calls. Use build and workflow management tools. There are many of them out there nowadays. Make is quite an old-fashioned one, of course, Snake Make, and there are many more modern ones now. I think there are hundreds of workflow management tools out there which can help you automate repetitive tasks and create whole pipelines for you with repetitive steps. So the last guideline I want to give you here is to provide test data and tutorials to users. When you write a software, when you write methods to code, you usually have test data. You have probably plenty of test data. So make these test data available to your users, to other developers. And this is useful because you can assess whether an installation was successful. You can try and verify the whole functionality of a software. Other researchers really benefit when you give them test data. Make them and assign them to the code base. Make them publicly available in the Git repository. Very important. And well, nowadays you can explain software with a nice tutorial. You can either write a tutorial, give a written documentation, or a step-by-step tutorial. You can give it on a wiki page or within a PDF. But what you can also use is use modern technologies. You can make a video of describing your software. Of course, it takes a bit of time to get into that. But when you create a step-by-step tutorial in a video screencast with this format, it's also a lot of fun. And researchers who don't have the time to read really complex user manuals, they will have a very, very high benefit of that. So here I will give you my 3 favorite excuses that are frequently said as common arguments, frequently given as common arguments against best practices of software development. First one is that these high-level software development techniques do not apply to these domain experts, and we cannot expect that biologists, chemists, material scientists take up these high-level software development methods. Well, actually, as you've seen in the previous slides, it's not that hard to have a certain standard to use these guidelines, and they are very useful. And then second excuse is that there's no time to learn these techniques because we have to conduct our research, write publications, apply for funding. Well, this is all very true, that time is lacking in research, time is lacking everywhere, but when you apply some of these best practices, you will save time afterwards. Yeah, you will be more efficient when you automatize repetitive tasks. And when you can help others not to reinvent the wheel and not to rewrite every bit of code over and over again, because then you will actually have more time in the end as a researcher to apply for funding, to conduct your research, and to write publications. Yeah. And then the third excuse, don't make yourself so small. So like, we are not the industry, we are not the big players, we don't have big data and so on, so we cannot apply these techniques in research. Well, that's not true. These simple guidelines, these best practices to software development, they can be directly applied in research. So the challenges of research software nowadays is that research software is often developed as an in-house or community effort, and then it lacks the motivation and also resources for maintenance, documentation, and adequate infrastructure. This is a fact. Yeah? You don't have people for testing software tools, as it is often the case in industry. And in most cases, students and researchers do not have received any training during school or university times to perform sustainable research software development. This needs to change, of course. Yeah? So the funders and the institutions, the universities, need to acknowledge that and recognize that this is really important, that you can even be more efficient, you can save resources if you provide a sustainable research software development, and if you teach these to the people how to do that. Many researchers see themselves as primary users of a software, so there's not often an incentive or to invest in documentation portability. But what would be an incentive in research? Yeah? You can ask this question, discuss it, and what about making career path as research software engineer? So also here to the funders, this might be very, very important, and there are some funding initiatives now going on where research software gets actually funded for long-term maintenance, or at least for a maintenance for a couple of years longer beyond the research projects. So there's a positive trend nowadays. So as a summary, research software is one of the essential tools in science. Research software that is sustainable can prevent duplication of work and reduce a lot of redundancy, and therefore also then accelerate the research, because the people have more time to actually conduct the research when they have their software tools in place, and that the software tools are not buggy anymore and running correctly and are tested and so on. So the relevance of sustainable software developments is now being increasingly recognized. That's what I mentioned with the funders, institution funding bodies and so on. And the uses of best practice for scientific computing will help developers and users. So research institutions and funding bodies now need to support scientists for building better scientific software. And finally, I give you here some references that I use for preparing this presentation, and really some easy and nice reads. For example, the 10 simple rules for documenting scientific software, 10 simple rules for developing usable software in computational biology, and there are some good and best practices in scientific computing listed here. And on the next page you can find some classical reads on agile software development, here by Kent Beck, who's quite famous in the field. and some on the code conventions and so on. So sustainable software development, I think, is gaining a lot of momentum nowadays, and I thank you a lot for listening to my talk. And yeah, so my name you can find here. We have a section who's actually in the interdisciplinary field between domain experts and also the IT department. So software development and sustainable software development is will be one of our core tasks here at BAM. And yeah, I thank you a lot for your attention.